Screen sharing. See if this works. Okay, you seeing my screen okay there?
Yep, we do.
All right, let me just something for myself here.
Just a quick note, if anyone has any questions during the talk, they can leave it in the chat or wait until the end to to ask the questions. This whole talk will be recorded. The Q&A session won't be. Thanks.
All right, just trying to get the right things on the screen here. I'm just about managed it, but Zoom is somewhat confounding in the way that it works. All right, I think that will do. I was trying to see myself on the screen, but that seems to be...
Oh, that's hard. That's really hard.
Yeah, well, forget it. I've seen myself before, so that's all right. So first of all, thanks very much for inviting me here. I wish I could be there in person. Actually, I know this is a very beautiful region of Canada. And one thing I should say, though it's entirely misleading, is that I actually grew up in Banff. But that's Banff in Scotland, not Banff in Canada. And Banff in Scotland is a little fishing and county town of about 3,000 people when I grew up in it. But that's the one that gives its name to Banff. And lots of Scots and lots of my distant relatives ended up in Canada. Anyway, enough of that. As I say, thank you for inviting me to talk to you. And I'm going to talk about self-configuring silicon photonic circuits here. So let me get that on the screen, right? Okay. So what do I mean by this? Well, we can make very complicated silicon photonics now. And one of the issues with that is if you really wanted to exploit that complexity, you'd actually also have to be able to control it. So as I said, silicon photonics lets us make very complicated optical circuits. We're essentially using the technology of silicon electronic manufacture and repurposing it to make optical circuits. And it can make very complicated things with silicon waveguides and silicon dioxide claddings and things like that. And one of the things it allows you to do is to make very complicated meshes of interferometers. So normally no one in their right mind would do that. No one would make a system with a whole bunch of interferometers in it because it's very difficult to connect them up and control them. And I know people have actually tried to make complicated interferometer systems with bulk optics and they simply didn't work. And it turns out, though, if you think about meshes of interferometers, there are many interesting things you could do with them. And in fact, they allow us to make a kind of universal linear optics that is well beyond conventional optical systems. We can think about doing things we simply couldn't do before. So, as I said, it could be very hard to control these, however, and hence people had not really looked at this much before. But a key trick is that we discovered that there are specific architectures of interferometers, meshes of interferometers, kind of like a chain link fence of interferometers, that can correct, stabilize, and configure themselves based on very simple algorithms. These are very simple progressive algorithms. You just optimize one thing at a time. Basically, you're looking at the output of one photodetector and adjusting one element. And since we discovered these architectures and algorithms, we therefore have a way of working with very complicated interferometric circuits, and that opens up a whole new class of optics to work with. One of the nice things about these is the algorithms are so simple, they can actually adapt the interferometer network, the entire thing. They can adapt it to the problem of interest in real time. And I'm showing you down at the bottom here, let me see if I can get my laser pointer thing to turn on. I'm showing you down at the bottom here an architecture I will come back to later on. So it's a bit complicated to look at the moment. But each one of these elements here, these blocks, are actually two-beam interferometers. And you can see in this, what I have here, I've got these waveguides. These black lines are meant to be waveguides. These are Mach-Zehnder interferometers, these blocks here. These elements here are detectors. And mostly, these will be mostly transparent detectors. So they just pick off a little power to look at it. And you see in this mesh I have here that there's actually 9 interferometers in it altogether. There's a diagonal line of 4, a diagonal line of 3, and another diagonal line of 2. And this is performing some operation on a vector of amplitudes, 4 different amplitudes and 4 waveguides here of light beams. and coming out with 4 different amplitudes over here. And it turns out we can do an awful lot with this, and we can actually control it, and we can have it set itself up. So I'll be telling you a bit about that. And specifically, as I said, in a strange way, these meshes allow us to make optical systems that are actually universal in a way that's beyond what we could do with previous optics. And that lets up, when I say previous optics, I'm meaning things like lenses and mirrors and beam splitters. It's not fundamentally impossible to do what I'm going to do with those. If we use these lenses and beam splitters and mirrors, you can fundamentally do what I'm going to show you, but you can't do it in practice because you can't line up the interferometers. But now that we've understood these meshes a little bit more, we've understood that we can, in fact, make universal optical systems in a particular sense. And that opens up opportunities in sensing and communications and in information processing. There's quite a lot of interest now in these for neural networks and for solving equations. And because photons have all these beautiful physical properties, we can use these both in classical and also quantum systems. There's quite a lot of interest in that. I won't talk about quantum systems today, but I'll show you some classical ones. So to understand what I'm talking about here, let's look at what is possibly the simplest kind of architecture we could have. And I'll describe this in more detail as we go along. But here's the kind of thing I'm thinking about. This is figuratively here looking down on the top of a silicon photonics chip. This is just a diagram I'm showing, but I'll show you a real one later on. And in this particular chip, what I'm showing is actually a whole line, actually 9 different interferometers here, and a bunch of photodetectors at one of the ports of each of those interferometers. And these interferometers are connected in a diagonal chain. And I'm showing here some grating couplers, or here possibly with some lenslets. But the idea would be you could shine a light beam down on this, and then magically, no matter what are the relative amplitudes and phases that are landing on these grating coupler patches, the light that is coupled into the waveguides is actually automatically coupled all out of this top waveguide here. It's what you could call a self-aligning beam coupler. So we'll look at how this works, because that gives you the basic ideas of what these mesh architectures are about. And we did not know how to do this before. That is to take an arbitrary input beam and couple it all to one output waveguide, a single mode waveguide, automatically. So here's the idea, and we're going to start by looking at just understanding Mach-Zehnder interferometers. What is a Mach-Zehnder interferometer, especially a waveguide one? So we're going to look at a Mach-Zehnder waveguide interferometer. So that is formed with usually 2 50-50, that is kind of equal beam splitters. And I'm showing you here waveguides. So here's 2 incoming waveguides, and in silicon photonics, these would probably be silicon waveguides. And they come close together down in here, and this forms what's called a directional coupler. So the light can leak from this waveguide down into that one over there. And similarly, the light can leak from here up into there. And actually, you design these so that this is like a 50-50 beam splitter. If you come in with light here, half of it comes out on this arm, and half of it comes out on this arm. And the same at the other end. So if you make a circuit like this with 2 50-50 beam splitters in it, you have what's called a waveguide version of a Mach-Zehnder interferometer. And to make what we want to do here, we need at least 2 phase shifters. So one, which we could call a phi phase shifter, is to control the relative phase of the 2 inputs. And the other is to control the relative phase on the interferometer arms. Now, what do I mean by a phase shifter here? Well, the simplest way to do this with silicon photonics is simply to heat up this region of the waveguide. So this could just be effectively a resistor close to the waveguide. And you pass more current through that resistor, you heat up the waveguide, and that changes the refractive index a little bit in the waveguide. And in turn, that means that we get a change in the phase delay through that part of the circuit. And as I say, we have another phase shifter here that controls the relative phase delay in these 2 arms inside the interferometer. So suppose then we shine some light into this, and we're going to shine basically what I'd call mutually coherent light, essentially light from the same source into both interferometer inputs. And the amount of light that's shining in may have different amplitude in the two guides, and it may have different phase in the two guides coming into it. So I'm showing here some amplitude coming into this guide and some coming into this one. And these will also generally have different phases in the two input waveguides. Then what we do is we adjust this phase shifter to minimize the power over here. So we do our best, we just fiddle about with the amount of phase delay in here until we minimize the power over there. And if we've done that, what we've effectively done is whatever light was coming in this guide and coming in this guide, we are interfering them as destructively as possible at this output port. That's what's going on. We are interfering them in antiphase. So whatever was the light from this one is interfering in antiphase with the light from this one. We've set this phase shifter to minimize power, and that's what we've effectively done. So we've got these two input light streams. Whatever is coming out here of these two streams, it's in antiphase, or out of 180 degrees out of phase at this output, once we have minimized the power in this way. Then what we do is we adjust this phase shifter, and this phase shifter sets what you could call the split ratio of the Mach Zehnder. That is, if I was just shining light in one port here, by adjusting this phase shifter, I could control whether it comes out here or comes out there or any combination in between. The Mach Zehnder interferometer essentially overall can behave as a controllable beam splitter, and how the power is divided up between the outputs is set by this phase shifter. So that's what would happen if I just shine one power in here. But anyway, I can adjust this theta phase shifter to set what I would call the overall split ratio of the entire interferometer. That is how much power from one input, how the power from one input would be split between the outputs. And interestingly enough, if these are 50-50 beam splitters, adjusting this theta does not adjust the relative phase of how these inputs appeared at the output. It adjusts the overall amplitudes of them, but it doesn't adjust the relative phase. So therefore, since we had already minimized the power here by adjusting phi, getting these in antiphase, then we can adjust theta to exactly cancel them out. That is, we now just set the relative amplitudes of these two input light beams, the relative amplitudes of them here, such that they exactly cancel. So that progressive adjusting of phi to minimize the power here, and then theta to minimize it again, we can take it right down to 0 here. And we've combined the power in these two waveguides, no matter what was their relative amplitudes and phases, and it's all now appearing at this one output. And that was a simple operation. We just adjusted one parameter at a time to minimize the power at this output here. So in a Mach Zehnder with 50-50 beam splitters, for any relative input amplitudes and phases, we can null out the power at the bottom output by two successive single parameter power minimizations, first using phi and secondly using theta. In fact, by making meshes of these Mach Zehnder's, we can use Mach Zehnder blocks with phase shifters in any two of these four configurations, as long as one of the phase shifters is within the Mach Zehnder, or one or other arms of the Mach Zehnder. Any combination of two will work as long as one of them is in here. So there's a few different configurations you can set up for this. I just wanted to point that out. So now that we've understood how to combine two beams into one interferometer so they just come out of one output, we can now take the next step, which is to combine these, for example, in a diagonal line or a chain. And the idea is we can progressively null out these interferometers one after the other until we're left with all the power in only one output. An interesting point about this is we don't have to calibrate anything, and we don't have to do any calculations. This is a self-configuring scheme. It just doesn't involve any calibrations or calculations. So let's see how this works here. Now I've set up a simple diagonal line of 3 Mach Zehnder interferometers with the output of one connected to the input of the next one, and it also gets another input from another waveguide. And then the output of this one is connected to the input of this one, and it gets another power from another waveguide. So you can see how this is going to work here. First of all, we're going to measure the power in this detector, and we're going to minimize it. So this detector, we're going to minimize the power in this detector by adjusting the corresponding phi, so that's this phase shifter, and then the corresponding theta, so that's this phase shifter, until we have minimized the power here, which means the sum of this power all appears here in the upper output of this particular Mach Zehnder. And then we keep going. What we do next is we minimize the power in detector D2 by adjusting the corresponding phi, that's this phase shifter up here, and the corresponding theta, putting all the power now from all three of these waveguides in the upper output of this Mach Zehnder. So it's all here now. And then we can keep going once more. We minimize the power in this detector by adjusting this phase shifter here, and then the corresponding theta, phi phase shifter, then the corresponding theta one. And that will put all of the power in the upper output. There's now no power going into any of these three detectors, and all of the power, no matter what was the relative amplitudes and phases in these different guides, is now appearing over here at the output waveguide. And that's our self-aligning beam coupler. And that's a function we just couldn't do before. There was no particular way of doing that before. And you see this is completely automatic. It can be completely automatic. So now we get back to the diagram I showed you earlier on. Here I imagine I've got 9 grading couplers, but you shine light on them, it puts light into the corresponding waveguide. And I have 9 of them here, and I've hypothetically connected them in a line. And then if I shine a light beam on here, or if I look at it in perspective, if I shine some big light beam on these lenslets here that focuses down onto these grading couplers, I can do a pretty good job of coupling all the power that gets into the grading couplers, at least, to this one output waveguide. And this could run continuously. I just keep running this algorithm sequentially, just minimizing the power in these photodetectors as I adjust the various phase shifters. I just keep running this algorithm. And even as the beam changes, it will keep coupling it all into the output waveguide as best it can, anyway, given the fact we're discretizing the system here to kind of 9 inputs. Incidentally, there's another architecture that works. That was a diagonal line architecture. There's what we could call a binary tree architecture. So here we have a 2 Mach Zehnders in this column and 1 in that column. And we could also extend this to the left. We could have 4 Mach Zehnders here and then 8 Mach Zehnders here and so on. This is quite a nice architecture. It's very compact. It's the shortest architecture you could do for this particular approach. And also in this system, it's possible to do the minimization at the same time for both of these Mach Zehnders. They don't interact with one another, and so you could be minimizing them, both of them at the same time, so it could be even faster. Now, that's an interesting little device, but the power of this scheme comes when we try to do something else, and this really is something we could not do before. Suppose now I have not 1 line of Mach Zehnder interferometers here, but 2 lines. And I've got detectors in between, but those detectors, I'm making them mostly transparent. I only need to pull a very small amount of power out of these, measure a small amount of power in these detectors. So most of the light will actually flow through these detectors. So let's see how this works. So we start out by shining a particular beam. It could be from grading couplers, but it's basically a vector of amplitudes, complex amplitudes coming into these waveguides. And suppose we've lined up this diagonal line here, so all of the power comes out this one output, output 1. If we were to shine a mathematically orthogonal beam in here, then it would pass entirely into these detectors, or through these detectors. Now, this is a rather fundamental point of physics, actually. When I say orthogonal, in terms of vectors, if you thought of complex numbers representing the amplitudes of the light beams in each of these 4 inputs here, an orthogonal orthogonal input would be one that if you form what's technically the inner product between those 2 vectors, it would be 0. And this is sort of basic physical significance. if I come in with an orthogonal input here, then actually none of it should come out of that top output. I come in with an input, line everything up, fix the alignment so that all the power comes out here. If I come in with an orthogonal vector of amplitudes here, then none of it can come out the top. And indeed, if it could come out the top, you could show that you could violate the second law of thermodynamics. You would be combining the power from two different inputs, two different modes into one. And you simply can't do that, because if you could do that, you could figure out a way of heating up a hotter body with two colder ones, and that would violate the second law of thermodynamics. So if I shine in what is technically an orthogonal beam here, all of the power in that, none of it can come out the top, which means it all has to come through these detectors. And then I see that I now have a second diagonal line here, and I can line up the second diagonal line using these detectors, excuse me. So all of the power appears in this one, the second output light beam. And as I said, we make these detectors mostly transparent. Then this second beam passes into the second diagonal row. That's this row here, where we self-align that to put all the output into output 2 here. And that has separated two overlapping orthogonal beams to separate outputs. And we did not actually know how to do that before. Excuse me here, I'm just going to quick drink of water. So now we're beginning to see that these meshes of Mach-Zehnders are opening up classes of optics that we simply didn't have before. Generally speaking, if I presented you with two overlapping light beams that were still mathematically actually orthogonal to one another, you don't have a general way of separating those out, but it doesn't violate any laws of physics to separate them out. And now these interferometer meshes are showing you actually how to do that. This is really a different class of optics. And you can keep going with this. We can add more rows here. Here we only actually have to add one more row in order to do this. And I can separate a number of orthogonal beams that is equal to the number of beam segments, or the number of waveguides that I have here. So that would be 4. I can actually separate 4 orthogonal beams to outputs over here. And this works for any set of orthogonal vectors. I set up the first row using the first vector, the second row using the second vector, the third row using the third vector, and I get the fourth one for free because there's only one other vector basically that's orthogonal to that that's left. It is also incidentally possible to do this with only detectors at the output. There is a version of this algorithm where you don't have to have the detectors in between, although then you have to sort of tear down the network in order to reconfigure it. You have to put the Mach-Zehnders into cross states temporarily in order to set it up. Now, if we put identifying tones on each one of these orthogonal beams, so I take my first vector of amplitudes here, and it's all come from one source at some point, and I put a small tone on that, modulated at a kilohertz or something, then I can have this line of detectors just look for modulations at 1 kilohertz. And I can do that for the subsequent ones. Maybe the second orthogonal beam I send in is modulated at another frequency, maybe 1.7 kilohertz or something, a small modulation. And the third one at some other frequency, 1.4 kilohertz, something like that. Then I can actually have this mesh continually reconfigure itself to separate the orthogonal inputs. And that's true even if the vectors change. And this is a remarkable concept here. So even when all the beams are present at the same time, and even if they're changing, I can automatically separate everything. And my Italian colleagues, basically Francesco Morochetti and Andrea Maloni and their various students actually made one of these chips. And you're looking at that here. Here's the circuit that I showed you. And here's the actual silicon photonic chip. And what they did here was they came in with 4 data streams on 4 different optical fibers. So channel A, channel B, channel C, and channel D. And they coupled them into grading couplers here. So they go onto this chip. And then they deliberately put them into a multi-mode guide. So they took all these single mode inputs and squished them together into a multi-mode guide in the middle. And that multi-mode guide actually mixes everything up. So what comes out of that multimode guide at the far end is all mixed up. Channel A is mixed up over all the modes of the guide. Channel B is, channel C, channel D. It's all mixed up inside this guide. And then you simply take that output and separate it arbitrarily into 4 waveguides again. So I've sent in 4 separate channels. They've gone through this multimode waveguide, sort of simulating a multimode fiber, for example. And everything is all mixed up. The beams are then separated out in some fashion into 4 waveguides here. And then I put one of these magic meshes here. And we have put little identifying tones on each of these channels to start with. I set up the detectors to look for those tones, and magically, I can separate everything out at the far end. This is really a completely bizarre concept. Imagine, for example, that I had 4 streams of water, 4 faucets or taps, depending on whether you like British English or American English, and I'm turning them on and off. So I've got 4 taps, and I'm turning these taps on and off, and I'm sending water out of these taps, and I combine it all into one stream. Everything's all mixed up. And then I pass it over a magic bed of gravel. So that's what this is. And it separates out the streams again. So I turn on these different taps at different times. I take all the water, I merge it into one stream. I pass the stream over a magic bed of gravel, and it separates out the 4 modulated streams again at the far end. That's the equivalent of what we're doing. It's almost magic, but this actually works. And if they come into this guide and this multimode guide in here and mess it up, that is, they heat it up. Actually, they heat it up by shining a short wavelength laser at it. That completely changes the way that the modes are mixed up. But the mesh just automatically settles itself to sort them all back out again. It's completely magic. So that gives you a sense of the kind of power that these meshes have. They can do things we simply did not know how to do before, and they can do it automatically. This, I won't go through the detail of this, but one of my colleagues, Joe Kahn, and his students, Karthik Chudagunta and Ian Roberts, looked at how fast this could be. That is, if we're only using some small power, maybe we're shining 10 microwatts of light into this mesh because we've gone through some long optical fiber system, hypothetically, how fast could we manage to reconfigure this mesh? And they analyzed this based on signal to noise ratios and detectors. And they concluded that, in fact, even with only 10 microwatts of optical input power, you could settle a 4x4 network like this in microseconds or less. So this entire network could reconfigure itself in microseconds to sort these channels out. That was their analysis. And that means you can work with kilometer scale multimode fibers. You can do free space turbulence compensation. You can also reconfigure rapidly for other kinds of operations, like these meshes basically are performing matrix multiplications. So you can change the mathematical operations you perform on them quite quickly. So we've seen that by working with these interferometer meshes, we can do things we simply could not do before in optics, including, as I've shown you here, adapting in real time in important problems. And there are many other things we can do with these also. For example, if we have a free space beam, so I'm imagining up here I've got a source, and it's shining light, and I'm collecting it. Here I've just shown 4 grading couplers coupling into a simple 4-element diagonal mesh. I've just shown them in a line here. But I've got a source here. It's shining light down onto this set of grading couplers. I can then combine that power as best as possible and send it all out this waveguide. And if I keep this algorithm running, I can actually track that source as it moves around, and also as it changes its focal distance. This doesn't just track in angle, it also tracks in focus. That comes for free in this kind of approach. And my colleagues in Italy have done some experiments showing these kinds of things. And you can also put in an aberrator of some kind, which could be atmospheric turbulence, for example. I'm showing it here as an aberrating plate. But this system will still do its best to combine all of the power that arrives at these grading couplers and send it out this waveguide. And incidentally, if I were then to send light back in here and back through the aberrator, it would take out the aberrations and I would focus back down on the source here. This is technically performing phase conjugation. Another intriguing idea is if I've got some unknown scatterer here, so I'm just showing you as some kind of cloud, and I have two of these meshes facing one another, I can actually iterate to find the best channels through that scatterer. So I start by shining light in this guide here. It goes through this line of Mach-Zehnders and comes out as some kind of wave, say the red one here. And it comes out of the scatterer as something else. I send it into this line of grating couplers, and then I do my best to line that power up out of this guide. And then I shine light backwards through this system and try to do my best to line it to get the most power back out this guide. And I keep going backwards and forwards here to maximize powers. Eventually, what this will do is find the strongest coupled channel through that scatterer. But wait, there's more. If I then shine light into the second line of Mach-Zehnders and do the same kind of trick backwards and forwards between the two sides, it will find the second most strongly coupled channel, and so on for the third and the fourth. So this will actually find the orthogonal channels through any scatterer, from the waveguides on the left to the waveguides on the right. And that's something we haven't tested yet, but I'm looking forward to starting to play with those experiments. Now, you might be saying, well, wait a minute, suppose these Mach-Zehnder interferometers are not perfect. In particular, one of the things that can happen with these is that the split ratio in the fabricated beam splitters is not actually 50-50. And if you don't have 50-50 split, you can't actually get perfect cancellation at the outputs, and that would limit what we could do here. Well, I'm not going to go through the details of it, but it turns out if you have some way of adjusting the split ratios after fabrication, then only by maximizing and minimizing powers in detectors, you can end up setting both beam splitters to 50-50. It's an interesting little algorithm, but I won't, as I say, won't go through it in detail. But it's another algorithm that works only by maximizing and minimizing power in detectors. So if you have Mach-Zehnder interferometers themselves functioning as beam splitters, so it's a little tricky, I'll show you a picture in a minute. The actual fabricated fixed split ratios of the beam splitters inside the Mach-Zehnder can be as bad as 85-15. And I could get this whole system to work as if I had perfect 50-50 beam splitters. And just to illustrate that, here's an experiment done by some of my colleagues in Bristol University. And here's a system down here. This is sort of 3 Mach-Zehnders in a row, but the first Mach-Zehnder here is functioning as a controllable beam splitter. And this Mach-Zehnder here is functioning as a controllable beam splitter. The actual physical beam splitters, the nominal 50-50, but they may not be, the nominal directional coupler beam splitters in here don't need to be 50-50. But by running this algorithm, you can make this Mach-Zehnder actually behave as if it's a 50-50 beam splitter and this one. And the proof here is in this experimental data. This is trying to measure the rejection of this Mach-Zehnder when you're trying to tune it to null the power out. And as fabricated, it only gets about 30 decibels rejection. But after running this algorithm on this system, we can actually get 60 decibels of rejection. It magically improves the interferometer. So we can have perfect optics from imperfect components. And note also, we didn't have to calibrate anything and we didn't have to calculate anything here. This particular algorithm is only based on power minimization and maximization as I adjust phase shifters inside these various Mach-Zehnder elements. Another thing we can do is to analyze multimode fields. Now, why would I want to do that, or how would I be interested in doing that? Suppose you've got a field coming at you with amplitudes in various different modes. Now, there are ways that we could split modes. If you've got fixed kinds of modes like Laguerre Gaussians or orbital angular momentum beams, there are known structures that will separate out at least those known kinds of modes. But that would only separate them out in a sense to give us the relative magnitudes in each of those modes. It wouldn't tell us the relative phases. And if we really want to know what a light field is, we have to know the relative phases. After all, it's the relative phases of light beams that allow us to form images. If you look at the light on the surface of your glasses, the light on the surface of your glasses just looks like uniform illumination. But it's the phase correlation between different pixels on your glasses that allows you to form an image. It's the relative phases that really matter. And in optics, we have not generally had a way of doing this. And part of the reason is we would need to interfere all of these different pixels with one another, and that would be complicated. Now, a standard trick is to use a separate coherent reference beam. This is how you make holograms. And if you shine a coherent reference beam onto something, then you can get an interference pattern. And from that interference pattern, with a bit of additional calculation, you can deduce what the original phase distribution also was. But you may not have a coherent reference beam. And if you're looking at a natural scene, for example, you don't even know what reference beam to use. You don't have anything that is necessarily coherent with this source of light that you're looking out there. It could just be ordinary so-called incoherent light shining back at you. You don't have anything that is necessarily coherent with that. So how would we measure the actual phases of all the different parts of a beam or the different modes in a beam? Well, here's one way to do it. We make one of our self-aligning beam couplers here. And the one I'm showing you at the moment is one actually using this binary tree approach. So this is 4 Mach-Zehnder blocks here, and another 2 Mach-Zehnder blocks here, and a final one over there. It's a self-aligning beam coupler. So I shine some light on here that I don't know much about, but I've calibrated this whole system here. So I know what the various settings I might put onto the phase shifters in these blocks. I know what it means. So I shine the light on here, and then I self-align this system so all of the power comes out of the output. Then because I know the meaning of all the powers, all the tuning that I've done, I know what the phase shifts are in all of these different interferometers, then I can actually calculate from that what the original beam was. So let me repeat that. I shine light on here, unknown light. Here I'm just showing 9 grating couplers. I then self-configure this device to put all the power at the output. Then I read off the settings of all the phase shifters here, and with a simple calculation from those settings, I can deduce what the original light beam actually was that I shone in. I have not required a phase reference beam shining in. I don't need that. I don't need an external reference beam, and I've now managed to measure the relative amplitudes and phases of all the different modes or pixels in the image. And I've done that, as I say, without any external reference beam at all. And you can see why it works. I've essentially, with this process, I have figured out the relative phases between all of the inputs. So I've figured out the relative phase between these two inputs in setting this interferometer, so all the power comes out here. And similarly for these two, and similarly for these two, and similarly for these two. And then with this interferometer, I'm figuring out the relative phase of these two outputs, and this one's figuring out the relative phase of these two outputs, and this one's figuring out the relative phase of these two outputs. So I've actually, by this chain of interferometers, managed to solve this tricky optical problem. As I say, we didn't know how to do that before. We don't need a reference beam, and we can manage to measure all of the amplitudes and phases in a light beam. I can also run this backwards. Now that I know the calibration of all of these here, I can easily shine a light in and generate any specific set of relative amplitudes and phases out here to come out of this magic set of grating couplers. I'll mention just a couple more things here. I don't want to take too much longer. Another point about this, I mentioned that these kinds of meshes of interferometers have a kind of universality to them. What I've shown you so far is actually technically what we call a unitary operator. That is, I'm representing a matrix as long as the matrix has got no loss in it. Of course, there are systems which are not like that. Most systems are actually not like that. But there is a way of using these meshes to implement any matrix. And I'm just going to show you briefly how we do that. And this is based on a mathematical idea called singular value decomposition. So I'll show you how to make that. I'll show you how to implement a matrix based on this idea of the singular value decomposition of the matrix. And that allows us to perform any matrix multiplication. So for arbitrary linear optics, for neural networks, for classical processing or quantum processing, I can now implement any matrix I like. And also I can set this up using these self-configuration techniques. So let's look at how this is done. Here actually is one architecture for doing it, for the case of 4 inputs and 4 outputs. So what happens is we have this mesh, which I've shown you before, that can couple any 4 orthogonal vectors of inputs here separately to each of these waveguides in the middle. And light in each of these waveguides can be converted by this similar chunk. I flipped it upside down, but this is also one of these arbitrary unitary meshes. I can have this mesh generate from light in this waveguide, and this one here, and this one here, and this one here, any particular set of 4 orthogonal vectors out there. So I'm able to convert from any 4 orthogonal vectors here to any 4 orthogonal vectors over there. And I can also self-align these schemes. I can train them with the vectors I want to go to. And also, one more thing, I can control the amplitude and phase in the middle of the light between, comes out of here and then goes into there. Now, why would I want to do that? This kind of architecture I'm showing here corresponds to being able to implement actually an arbitrary matrix with this mesh. At least if we don't require gain. We could put gain in here if we needed actual gain in the system. And because of that, this mesh is fully universal for performing any linear transformation. Now, how do I know that? Well, the mathematical reason this works is because for any matrix you can think of, as long as it's got finite elements, you can always perform what's called the singular value decomposition. That is, some matrix D, you can write it as the product of 3 things. A unitary matrix, that's one of these lossless matrices, a diagonal matrix, and another unitary matrix. You can always do that for any matrix, and it's actually not hard to do. It involves solving a couple of eigenvalue problems to do it. It's a very standard mathematical thing. The optical units in this mesh actually physically implement that singular value decomposition. So this mesh here is implementing this arbitrary unitary matrix. The diagonal line here is implementing the diagonal matrix, the diagonal line of modulators here, Mach-Zehnders functioning as modulators. And then this triangular matrix, this triangular unitary over here is implementing this second unitary matrix. So I've constructively made any possible matrix between the inputs and outputs, at least as long as I don't require gain. And another thing about this is this is really the first proof that any linear optical component is possible. That is, you can prescribe any linear mapping between the inputs and the outputs, and we now know that you can make it. And we didn't know that before, because lenses don't do this. Lenses aren't nearly as universal as this. And another strange thing about it is it proves to you, strangely enough, that you could write down any linear optical component as a set of 2 beam interferences. And I don't think we knew that before. Now, is that useful for anything? I'm not quite sure, but the idea of being able to make these arbitrary matrices is rather intriguing from the point of view of doing information processing. And also, we can use these in thought experiments for fundamental proofs. And I won't spend much time on this, but I'll just mention a little bit about it. Another drink of water here, if I may, excuse me. We can also flip this logic around. We can always perform the singular value decomposition of an optical component or system. If I have a linear system, any combination of bits of glass and waveguides, whatever, if it's linear, then I can write down the relation between the inputs and the outputs, if you like, as a matrix. And I can always perform the singular value decomposition of a matrix. And that means that any linear optical system can be described as a mode converter. That is, it converts from an orthogonal set of inputs to an orthogonal set of outputs. And these sets of modes that you get out of this turn out to have basic physical significance. Let me just say a little bit more about this, and then we'll come to a conclusion. Suppose that we think we've got some source space here, and I've got some source function in it. I've written this using a Dirac notation, but don't worry about it. It's just a vector of amplitudes, if you like, that defines some set of sources in here. And it gives rise to some wave in a receiving space. And again, I've written this in a Dirac notation, but it's just a vector of amplitudes, if you like. This could be free space communications or any scatter or optical device or object between the spaces. Whatever it is, it's just describable by some linear operator that relates the set of amplitudes in here to the set of received waves, received amplitudes over here, set of source amplitudes to set of received amplitudes. So mathematically, the vector of output amplitudes, the received waves in here, is just some linear operator times the vector of source amplitudes. Because we can always perform the singular value decomposition of any linear operator, we have therefore discovered what we call the mode converter basis set of functions for this optical system. That is, it's a set of orthogonal source functions that lead one by one to a set of corresponding orthogonal received waves. In turn, that means there is a set of orthogonal channels for communication through space or through any linear scatterer device. And they're given by these so-called mode converter input and output function pairs. And these are unique, and they give you the best possible channels. It's a surprising conclusion. No matter how complicated an optical system I have, if it's linear, there is a set of orthogonal channels through it. And the system can be completely described in terms of those orthogonal channels and the amplitudes of the couplings involved with it. Now, that may not seem to have much importance, but let me just briefly list some of the consequences of that. Among other things, first of all, this allows us really to decide what are the best channels for communicating. There's lots of discussion about this problem. If I get two free space systems, a set of sources over here and a set of receivers over there, what are the best channels to communicate between these surfaces? There's a lot of discussion about orbital angular momentum beams, for example. But in general, those are not the optimum answer to this problem. But there is an optimum answer to this problem. And you can actually figure it out. And the system that I showed you that went back and forward between inputs and outputs to find the best channels, that was actually physically performing the singular value decomposition of the piece of optics. So you can always find these best channels, the mode converter basis sets, and I've even shown you how to do it with these meshes. So we can, in fact, define the number and strength of coupling of the best possible channels, and not necessarily orbital angular momentum beams, it's not necessarily anything in particular like that, but it is mathematically well defined. A few other things we can do with this, and all of this is discussed in this longer paper here. You can generalize diffraction theory for all sizes and shapes of objects. We have the most economical description of any linear optics. And if you work with these mode converter basis sets, it turns out you can rewrite Kirchhoff's radiation laws. Kirchhoff's radiation laws tell you that the absorptivity and emissivity of a surface have to be equal. The amount of light that it emits has to equal, relative to a black body, has to equal the fraction of the light it absorbs. We can write down modal versions of that, which we simply didn't have before. And we now have Kirchhoff radiation laws that apply for nanophotonics and even for non-reciprocal systems. So that's rather fundamental. You may have come across Einstein's A and B coefficient argument. It's a common argument relating spontaneous and stimulated emission. It turns out we can write an argument with only one coefficient in it. It doesn't need A and B, it only needs one coefficient. It's a mode by mode version of this, and it applies to these specific mode converter basis sets. And also, it turns out we can do a rather nicer quantization of the radiation field in any volume if we work with these specific mode converter basis sets. Anyway, I won't go into the detail of that, and we're getting towards the end of our time here. So let me just draw some conclusions. I hope I've illustrated for you that self-configuring photonics enables complex circuits for new optics. The algorithms we can use to run these circuits and also incidentally to calibrate them are simple and fast. And we can also use these algorithms to control the systems, which otherwise we would not want to do, with complex interferometric systems. There are many potential uses of these. We're basically just starting to figure out what we can do with this because we couldn't do this before. And these ideas I talked about also complement a fundamentally new way of looking at optics. The idea of these optimum communications channels or communications modes and these mode converter basis sets from this mathematics of singular value decomposition. Incidentally, I'm always very happy to send people copies of view graphs. Just send me an email. My email is very simple, dabm@stanford.edu. I'm happy to acknowledge my funding from the Air Force Office of Scientific Research. And there's a whole bunch of references here that we could talk about. Though it's obviously too small to read on this screen. But again, if you ask me for it, I'm happy to send you the slides here. So let me come out of this mode if I can get this thing to go away. I've lost my, here we are.